Hey TJ Machine Learning Club. This is my lecture on Ensemble Learning from TJ Machine Learning. So, starting with the intro. Ensemble Learning and Machine Learning is basically a methodology where you combine numerous different machine learning models to help improve the overall performance of your model. So, you take, for example, a decision tree, combine it with an SVM's output, combine it with a k-means clustering algorithm output, or something like that. And in the end, you'd combine those decisions together to come up with some sort of kind of voted or kind of aggregated output. So this technique's normally used to improve either classification, prediction, or even function approximation for a model, and it can also help reduce the likelihood of selecting a poor model. So what I mean by this is, say you're having like a machine learning problem and you have a certain data set, right? For example, say we're looking at like the Titanic data set. Now, instead of just kind of going at it, just saying, I'm going to try to use a neural network to classify whether or not these passengers will survive or not. Instead of trying to do something like that and just kind of guessing on which model would be best, using an ensemble would help you kind of get the kind of help you figure out what exactly is the best model or so, because you're kind of combining the numerous models together, and there's a higher chance that at least one of the models you've used in your ensemble is the model best fit for that data. So this approach in general allows to the production of just better overall performance compared to just one single model, although there all are downsides, for example, like high computational time and memory, and of course. So just to kind of visualize it, it feels a little bit confusing how I started off. This is kind of just like an example of an ensemble learning here, where we have this training data set, and then we kind of split it up into numerous samples. This is one type of ensemble, where you'd split it into numerous sample data sets, take different samples, and each sample goes into its own classifier. And at the end, the outputs from each classifier would be put into some sort of meta classifier, where you kind of make another final prediction based on the previous predictions at this aggregation stage over here. So this is kind of just like an example of a bagging algorithm, which we'll kind of discuss a little bit more later. But essentially, we're able to kind of combine numerous classifiers, sample the data a little bit more, and kind of go a little bit deeper by like using the outputs from these classifiers to train another classifier, which is kind of interesting. As you can see, this is kind of explains how it would take kind of longer for these algorithms to work or so. But ensemble methods just in general have performed like really well, I think, over the past couple years in lots of machine learning competitions, and they're gaining like prominence. And the like one of the most like famous instances of the ensemble methods were in the Netflix prize competition, which was a $1 million competition to develop the best algorithm to predict user ratings for movies and TV shows on Netflix. And the winners used an ensemble model to even like beat Netflix's algorithm itself. So that's something pretty interesting. Um, okay, so what are ensemble methods? Ensemble methods are meta algorithms that combine several different machine learning techniques into one predictive model to either decrease variance, decrease bias, or improve predictions. So I'm not sure if you guys remember from, I guess, last year's machine learning meetings, but essentially just a quick review is bias in machine learning is like the inability to learn patterns, or essentially just be thought of how inaccurate your model is, or how like the ability of your model to like kind of it's not able to discern the patterns in the data. Variance can be thought of as the amount that like the your estimate from your target function would change if you use different training data. So essentially your variance could be thought of as like how much your model is overfitting on this data. As you guys might have experienced with your own machine learning models, if you have a really large model with lots of different layers, you might experience very low bias, so like high accuracy, but extremely high variance because it's kind of overfitting on this data. So, kind of in machine learning, the goal of like kind of your machine learning project or whatever you're trying to do is to kind of reach that bias variance trade-off where because you can't really have no bias, no variance. It just can't work like that just based on how the more complex your model is, the more likely it'll have a higher variance and thus a lower and thus also have like a lower bias. So if our model is too simple, has very few parameters, it might have high bias and low variance. But also, if our like model is too large number of parameters, it's gonna have a high variance and low bias. So basically, these three techniques, bagging, boosting, and stacking, are the most common ensemble techniques. Bagging is a technique to decrease variance, boosting helps decrease bias, and stacking just helps improve the overall predictions. And it's kind of like a mix almost. We could talk about that. And the ensemble methods can be divided into two major groups, sequential and parallel ensemble methods. So bagging and boosting are kind of in those categories. So starting off with sequential ensemble methods. So boosting is actually an example of the a sequential ensemble methods. And what a sequential ensemble method essentially is it's a method that where you take advantage of the dependence between the base learners, where, for example, it's like a learner suggests a prediction here where it says which is way off from the correct prediction. And then another learner uses this new prediction by kind of correcting it, and then it'll make its own new prediction with less error. Then another learner will use this previous prediction and so forth until I guess your model goes on for. It's kind of like an easier, simple way to think about it is like if you have a classroom of students and they're all discussing a problem and you're kind of getting the solution by just adding on to like the previous student or kind of going off of what your last student kind of answered. So this way the base learners are complementing the results of the previous learners. So these methods are known as boosting methods. For example, if you guys have heard of ADA boost, that's a really common algorithm. You guys should check that out. But essentially, these boosting methods or these sequential methods are meant to have very low bias in the way that you're kind of going through, you're kind of like learning, you're putting your training data into a model and then using that output in another model and so forth and so forth. So you guys can probably imagine that that would result in a very high variance, which is, I guess, the downside to boosting. So this is just to visualize what I've been saying before, where, well, like I was saying here, a learner suggests a prediction, which is way off, then another learner uses this new prediction. So here we have the original data set, which is going into our model. Then our model will go to another testing. It'll find these errors, and these errors will be used to train another model and so forth. And there's multiple ways that you can get your final output. Either it can be from this final learned model, or it can take some sort of voting or aggregation of all of the models that you've used so far as results. This would help, lower like the overall variance, because if I only use this final model for my actual like output, I would have a really low bias because this is probably the most accurate, but a very high variance because this has been kind of trained on the specific errors of this data. So using an aggregation of all of your models so far might help. It might increase the bias a little bit, but it would definitely lower the variance as well. So there's a trade-off there you have to consider. Um, so moving on to parallel ensemble methods, we have bagging. So these methods are a little bit different. They're sort of like you could think of as a path of democracy, where the different methods take advantage of the independence between the base learners. So each algorithm or so isn't really connected to each other. So these algorithms allow the base learners to make predictions, and then each of the outputs from like these different models would kind of be voted on, or sort of like the most common output would sort of be like the overall output of your model. So, for example, it will look something like this, where you have your data, you split it or so into three random subsets, or you just put the raw data into three separate models. That's another option. And what would happen is that you'd go through each different model, and then in the end, the results would be somehow aggregated. Say this was it wasn't really like a classification problem, and it was like a regression or so, then you could aggregate the results, take the average, something like that. Or if it's a classification problem, you can just take the vote of if this gave a 1, this gave a 1, this gave a 0 as an output, your overall would most likely be a 1 here. And this would give you this final prediction. And so, yeah, you could basically use different samples of the data. And the basic motivation of these parallel methods is to just kind of use the independence between the base learners, since that error can be really reduced dramatically by averaging all sorts of models. And one really common example of parallel ensemble methods are random forests, which might not have thought of before, but where like each decision tree is essentially working in parallel with each other, and in the end, your final output is almost like just a combination of all the decision trees combined together, which is, I mean, I guess why we call it a random forest in general. Okay. So now we're going to move on to stacking. So stacking is an ensemble technique where you kind of combine the different um, classification and regression models via this sort of meta classifier or meta regressor. So you're going to put lots of different regression models and in the end use the outputs of those models to create some sort of meta classifier. So the previous base level models are going to be trained on like the whole data set, and then that meta model, that final model, would be trained on the outputs of the first model as new features. So there could be like lots of different learning algorithms. So these are kind of two examples. So in this first example, you could either have the data going through the different base learners, different algorithms, and then each of them would give their own prediction, which would now these features would be used in some sort of meta learner to determine a final prediction. Or you could, for example, just put the data, again here, three different models, and create this stacked data set is what they call it. And that stacked data set from the kind of the outputs and the errors of the previous models would be put together, combined into a meta model to get these final predictions. So this is almost like a combination of this kind of parallel structure here, but then you're also using this sequential structure here where we're kind of using the predictions from one model into another model. So I like to kind of think of it as a sort of mix, but it's not really a sequential or a parallel method. So just to kind of quickly reiterate, parallel methods are like bagging, though that's an example of a parallel method, while stacking is an example of a it's like a different category, and boosting is a sequential method. Okay, so now we're going to move on to just the overall advantages of using ensemble learning. So when you have too much data, ensemble methods can actually be really useful when dealing with like all this data, or even just when you have like a little bit too much data, or you don't have enough data, because when this amount of data is really large to make like one classifier training difficult, the data can be partitioned into these smaller subsets, and each subset would be able to kind of be put into another like model or so, because it could take way too long or something if you trained a large, use lots of data that's kind of unnecessary on a simple model. On the other hand, if you have too little data, now if I kind of take samples of the overall like little amount of data and kind of use all these samples in different methods or in different models, it's almost like we're taking that original, say it was 50 lines of data, right? And we take samples of 20 lines and we make five of these models. It's almost, I mean, it's not really, but it's almost like we have now 100 lines of data rather than 50 lines. In this way, like we'd be able to kind of, it's almost like each data was drawn independently from the distribution. So another advantage of ensemble learning is data fusion. And in many applications that call for automated decision making, it's really common, like in the real world, when you receive data coming from all sorts of sources. You might have some sources, you might have data about some patient, and here's their MRI, here's this scan, here's their demographics, age, race, things like that, right? And in order to combine all of these methods, you can't feed in and like an MRI and like written textual data on their age or stuff like that together normally. It's more difficult to do that in just like a basic neural network or something like that. So what ensemble learning allows you to do is it allows you to make a separate model for your MRI data, a separate model for your demographics, and then in the end you can combine these outputs from the different models together in some sort of meaningful way to extract the important features from this data. And this combination of information is known as data fusion, and it can just lead to improved accuracy since we're able to use a larger variety of data. This is just an example I found where you have sensors, different sensors here, and each sensor kind of goes into some sort of pre-processing. You develop the features, and you put that overall feature vector into these like different models, and in the end, you kind of get you're able to put it in that final ensemble algorithm. So this last advantage of ensemble learning is confidence estimation, because the way this ensemble model works, right? Either we're, learning from previous models, or we're taking like a vote of all the model's outputs together, something like that, right? So this structure itself allows us to like assign a sort of confidence to our decision. So what this means is that, say like in the examples before, let's see, like these examples where we have like multiple different trees, right? Now, say both of these say one, this one says zero, and in the end, we're gonna predict a one as our output. But what like confidence estimation helps us do is we figure out, okay, how confident is our model that this is going to be a one? So in this case, it would be, say, 67% confident. If we had all ones and then our aggregation would result in a one, we know that our model is essentially 100% confident on our output. So the more confident in general, just more confident, or like if the majority of classifiers agree with the decision, this outcome can be interpreted as having very high confidence. And normally, if you have like half of the classifiers making one decision, the other half making another decision, this can be interpreted as the ensemble having low confidence. And in general, having a high confidence normally leads to just a higher accuracy in general. It's kind of intuitive. So here are some of the major disadvantages of ensemble learning. So first off, we have a reduction in model interpretability. So what this means is that since the models have become much more complex and we're using a lot of different features with our data, it makes it really hard in the end to determine, like, for example, what data was meaningful for our model, or like what exact part of our model, where did our model kind of get this high accuracy from? Did I need to use all these models together and take an average, or was one model essentially getting the right answer all the time? Um, like another common thing that a lot of that's very common in machine learning is to do like permutation import or feature or permutation importance, and determining which factors played a role in your final output, and like which if you have like 10 rows of data, and each of these 10 features are used in that final output. And then when normally with feature importance, you can kind of determine which features played a large role in determining whether or not, or like determining that final output. But with ensemble learning, it's much more difficult to do that. Another disadvantage is that selecting these models could be really hard to master, because normally what happens is there's a lot of like these common data sets might have some sort of data set, some sort of model that works best. Like this model will beat out all the ensembles of other models combined. So say there's a certain data set that just works perfectly with like SVMs, and now you're going to create an ensemble with KNNs, SVMs, neural networks, things like that. And what would happen is your accuracy would not go up; it would probably just go down with ensemble learning, because that data just happens to be fit for like an SVM. So, that's kind of just an example of where ensemble doesn't really help you in that way of finding that um finding that best model. Although it does help you kind of, still get that really high accuracy, but I guess if you're looking for the best possible accuracy, in some cases, ensemble learning could hurt. Finally, the most important thing is that ensemble methods are really computationally expensive, so they add lots of learning time and memory constraints to these like problems, and makes it really difficult to use ensemble methods in the real world, because say you're already training some large data file, almost like a gigabyte or something like that, and it takes days to run. Now, if you're using ensemble learning and you're stacking different models on top of each other and you're having a sequential, something like that, it would take so much longer. And just because of that and just memory constraints, it would really just be not applicable in the real world. Okay, so these are just some of like, just to kind of wrap it up here, some very common algorithms based on bagging and boosting. So a really common bagging algorithm, that's what I was saying before, was random forests. And these are just some boosting algorithms that you guys can kind of check out a little bit more. Eta boost, gradient boosting machine, XGBoost, and light GBM. And so these models you can just kind of little bit understand, but these are one of the most common bagging and boosting algorithms. But yeah, that's pretty much all we have for Ensemble Learning. If you guys were kind of confused towards the very start of the lecture when I brought up the kind of bias variance trade-off and things like that, I have on my PDF on the website, the PDF lecture, it goes a little bit more in depth on the bias variance trade-off and a little bit if you guys got a little bit confused, and it also kind of explains that kind of distinction between sequential and parallel, and kind of shows a little bit more examples if you guys are interested. And at the end of the lecture, I had added some like nice links where I got a lot of information, kind of some newer advances in ensemble learning. So be sure to check that out. But thank you guys for listening.